Continuing in our exploration of galaxies, we're going to talk about the cosmological principle and Hubble and galaxy groups and clusters and superclusters and all of those kinds of things. So Edwin Hubble was working at Mount Wilson. We keep talking about Hubble because, well, he sort of was a visionary, but he was working at what was at the time the two largest telescopes in the world, the 100-inch and the 60-inch at Mount Wilson. And so the field of view on those, meaning the piece of sky that you're looking at, is incredibly small. With the 100-inch, in order to photograph the entire sky would have taken more than a human lifetime. So Hubble took 1,283 sample areas and created a print of each and counted the number of galaxies in each of those. And because he used such a large number, he figured that he would get a good sampling of the sky. And so he figured out that the universe is both isotropic and homogeneous. So what does that mean? Well, that means that the number of galaxies that we see increases with the faintness of the galaxy. Well, we would expect that. If we are taking a photograph of, if you're sitting on, standing on the floor in a crowded stadium, and you take a photograph, the closest people to you are going to take up more of the photograph and be brighter because they are close. Far away people are going to be dimmer because they are not as close. And so that's isotropic. Homogeneous, in every direction we see approximately similar numbers of galaxies. So if we look at our local group, so in this image, the top circle fits into the tiny little circle down there on the bottom circle. This is similar to those blow-ups that we see of the solar system. It's very hard to get the orbit of Neptune on the page and still see the orbit of Mercury. So we blow it up into two different scales. So this is centered on the Milky Way galaxy. And, if we look out at our local group, we see approximately 60 members. There have been some new ones since this map was made that have been discovered. And we see 3 large spirals, and most of the rest of them are small irregular galaxies and dwarf ellipticals. So our local group is not that big, and we are spread out over approximately 3 million light years, and you'll notice from this that when the line goes up like this, it's showing you that, this galaxy is above the plane and below. So we have galaxies spread out, but also in 3 dimensions. The Virgo cluster, many of the galaxies in it are very faint and hard to detect, contains several hundred galaxies. This is the clusters are defined as either rich or poor, and the Virgo cluster is the closest cluster to us that is considered rich. Rich meaning lots of galaxies. The Virgo cluster is at a distance of 50 million light years from us, and it's actually only considered moderately rich because there's only a couple hundred galaxies in it. The Coma cluster, in comparison, is very rich. Diameter 10 million light years, but there are 10, 20, possibly as many as 30,000 galaxies in here. It's been counted several different times, coming up with different numbers. When we look at rich clusters, where they are very closely combined, what we find is lots of elliptical galaxies, very few spirals. In these rich clusters, you'll find spirals out on the outer edges, but not in the center. This supports our theory that ellipticals form when galaxies collide. And so when they're closely packed together, it's more likely that they collide and coalesce to form these giant ellipticals. So I've been talking about gravitational lensing, so let's, think about gravitational lensing, and I'll actually explain it. So we have a quasar. Light from this quasar spreads out in all directions, as light does, and as the light is spreading, it comes near this galaxy. And the galaxy is so big that it bends light. And so the light, as it passes this galaxy, this light ray gets bent a little bit, and this light ray gets bent, and so they both arrive at Earth. But if we look out, we assume that this light ray came from over here, because we're assuming that, light is straight. Light should be straight. Light is usually straight. And so when we take a photograph, we'll find that picture of that quasar here and here. And it's very difficult to tell that quasar, that light came from the same quasar. We have to know something about the galaxy in between, and then we can figure out, oh, this is all the light from the same quasar. So when we talk about gravitational lensing, Einstein cross is something that often comes up from that. So light from a galaxy far behind this galaxy is being bent around that galaxy. And so what we have, here, 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 and here is a supernova that we are seeing in 4 different places around that galaxy. The blue is the host galaxy that's been all stretched and warped by the bending of light. Einstein is the one who suggested that Einstein crosses should be possible. He also suggested that we would never be able to observe one because, bending light would just be too difficult, or recording the bent light. So the first gravitational lens was not actually recorded in a photograph until 1979. Just cool date. So, talking about famous scientists, this time we have Margaret Geller. And she realized that in order for us to better understand the structure of the universe, we needed to have much better surveys of where all the galaxies are in the universe in order to be able to understand how they're moving against each other. And she was instrumental in setting up several surveys of galaxies and working on 3D mapping galaxies. So one of the things that she worked toward was the Sloan Digital Sky Survey, and a number of the images that we have looked at today are images from the Sloan Digital Sky Survey. And so here we see one of the telescopes in front of the Sacramento Mountains in New Mexico. But the thing that's cool about the Sloan Digital Sky Survey is that it can image so many objects at one time. So what happens is that they take a picture of the sky and then create a metal sheet with a tiny hole in it where each object is on that plate that then is put on top of the telescope. And so one of these wires, fiber optic tubes, there we go. Sorry about that. One of these fiber optic tubes goes from that plate that is now only seeing one object, and it goes to a CCD device. So, each CCC device can record the information from a couple of objects at a time, but this allows them to capture light from 640 individual objects and be able to discern one from another. So massive amounts of data. Each night of observation, they record like a terabyte of data from all of the objects. So just crazy. And so the Sloan Digital Survey was able to create a map. So this map corresponds, the center of the map corresponds to the Milky Way, and then this gives us a redshift, which gives us an approximate distance out. The circle around the outside is at a distance of about 2 million light years. And then each dot is a galaxy. They are color-coded by having, red galaxies are older stars, and so as we look out, the stars become progressively older, which kind of makes sense, since remember, as the light comes to us, it takes time. But we notice that the red galaxies get more and more strongly clustered. So close to us, it's very hard to see the structure in the universe, but the farther out we look, the more we can see filaments of thousands of galaxies in a filament and then holes in between. The two black triangles correspond with the plane of the Milky Way, where we can't see out of our Milky Way because, well, there's too many of our stars in the way. And so I'm going to finish up this chapter on the next video.